Alright, we're going to introduce the idea of vectors here as we move pieces around and deal with some kind of real world problems with oblique triangles and how they work. So a vector is defined as a quantity that has both magnitude, which is just a size, and direction. And so that's just an angle. So there's a vector, right? It has a certain size from here to here, has a certain angle that we could create. So usually we represent them with arrows. And so we have a tail, that's the starting point. We have a head, that's where we end, right? And that vector in this direction is going to be different than one that's the same length in the other direction is different than one there. So it's unique in that piece of how it goes. We have some notation that's called the magnitude. That's our vector A. So we would say that's the actual physical thing, vector A. And then the magnitude, the length, is given to be in terms of our direction. So we have some angle, right? We're going to find something called unit vectors, I and j, that are 1 unit horizontally and 1 unit vertically. So we go over and up, just like you would on a coordinate plane. So you go over 1, that's an I, over 2, that's 2I, up 1, that's going to be a j. So we'll see how that works, and we'll put things in terms of I and j as we move forward here. The reason why components are necessary is we can break something like this into a right triangle, and we know a lot of stuff about right triangles. So that's vector v, that's my angle theta, and so instead of x and y, we're going to break those into our pieces. So x over the magnitude of v, so that's this actual length, that's all we're talking about, is going to be our cosine value. So cosine of theta, just adjacent over hypotenuse in terms of vectors, becomes x over the magnitude of v, or x is the magnitude of v cosine theta, just multiplying. We can do the same thing with y, and we get y is v sine of theta. And so we can scale these, right? We can increase or decrease these vectors in this magnitude by multiplying a number. So we just scale it, make it bigger or smaller by just having a value that we multiplied out by. So for example, 2 times vector v would be twice as long, but right in the same direction. Half as big would be half as big. And so we can talk about just scaling these unit vectors. Having twice as many unit vectors horizontally and vertically would give us a scaled value of twice the amount for v. So in general, we take off those values. X is just scaling I and scaling and Y is scaling J, and so we talk about in terms of I and J. Again, the same principle as before. And so we can then break that into just sine, cosine, and b, so we get rid of the x piece, right, just using what we did up here to substitute in, and we can make our values look like this. So our vector v is expressed in terms of these unit vectors I and j, and those get scaled by some amount x and y to give us the whole vector v as we go forward. All right? So we got to think for a second about what does it actually mean to add these things, like what is happening here. We can see kind of how that's working. I would go across, right, and then another tail would start here, and then another head, another tail, another head, another tail, another head, another tail, and eventually I get up to there. And so that's our general way of how we would do this geometrically. So to add vectors, we take a vector, we imagine we're pushing on some object, right? And we push it in that direction, and we can see that it should go that way. We're going to assume that our vector is strong enough to kind of move that thing. And so if I have another vector b that's pushing on the object there, we can all kind of guess that this thing is going to go off in that direction somewhere, right? It's not going to go down and to the left. It's going to move up and to the right to an extent. And that extent depends on how big a and b are in terms of their magnitude. So that's our resultant vector. That's how they go together. One way that we would do this is to construct our addition. Looking at it geometrically, we're going to talk about constructing like a parallelogram or looking at components as well. So one way to do that, there's my a and my b. To do it geometrically, what I would add is the head to tail. So I'd take a plus b, there's a, there's b, and then the resultant is over there, that's c. So the key part is it doesn't matter if I push all a this way and then all b that way, or do it all at the same time. The resultant is going to be the same. I'm going to go along this path vector. See, that's where we're going to end up. All right. So that's one way to do it. The key thing is that we don't put two vectors going tail to tail or head to head, right? We go here, then here, results in our green vector C. If we went the other way, so B then A, we'd see we get to the same spot. So it doesn't really matter. It's a commutative property for vector addition, just like if we add numbers. All right, so same thing as we go through it. So addition is commutative. It goes back and forth. Doesn't really matter which order it is. Algebraically, it's the same idea, except we need to figure out our components. So I'd have two angles, and then I'd have two for vector A and vector B, and then I'd be able to solve this in terms of components. So really I'm just adding up how much over is this one, how much over is that one, that's how much over total I'm going to go, and then the vertical component, right, how much up and how much up, that's how much I'm going to go over through that as well. So one way we could look at that, right, if we were to try to sketch it out a little bit more, would be to put those pieces on here. There's my vertical and horizontal, and then there's my horizontal components and vertical components. And I can see that if I'm just going up with those purple pieces, that's going to be my vertical displacement, and if I was to come across with my horizontal, those are my I values, that's my piece there as well. So again, geometrically or algebraically, it's the same principle as we move forward. You're often going to see these in terms of what are called bearing problems. So these have some direction attached to them, and the way that we define a bearing problem is north is 0 degrees, and then east is 90 degrees, south is 180, and west is 270 degrees. And so this is not like the unit circle, where east would be 0 degrees and you'd go counterclockwise. This starts at the top and goes clockwise through our directions. So if we had a plane was heading 50 miles per hour at 135 degrees, that is a vector, and so we could draw that in there like that and use that piece to be able to solve some word problems. If we had a wind was traveling at 50 miles per hour at 200 degrees, right? That's another vector that we can then use, and we would talk about, well, where is this thing headed? So we can think about it kind of as two pieces where we have the plane that's moving and then the wind is pushing on it. The key idea is that we make these things go head to tail as we go through it. So this is not to scale at the bottom, but it gives you a sense of kind of where your resultant would be. And that makes sense. If you were just to think about it, you're going in this direction and you're pushed over a little bit by the wind, you're going to end up down here, and that's what our green vector shows us. So we could solve it. There's my 500 and my 50. I'm missing an angle, and so I have to use the properties of both parallel lines and the headings that we've been given to find those angles. So I know that that's 45 degrees, so that has to be 45 degrees. And I know that's true because the whole thing was 135, and then there's 90 in that first quadrant. These are down here alternate interior angles from our geometry course. So those alternate interior angles, those are congruent, right? I can find that is 20, that has to be 70. And the reason that we can sort that out, right, is I have my 50 degrees that we were able to go, 50 miles per hour at 200 degrees. So this was 180, right? There's 200, that has to be 20. And now we have a triangle that we can deal with either our law of sines or law of cosines. In this case, we use the law of cosines to solve for x, and we just plug through the math part. So we'd set up our law of cosines and then plug through, and what we're going to do is we're going to find our value for x is 523 miles per hour. If I need to figure out the direction, then I got to find an angle. I'm going to have to use some inverse trig function to see if that's going to work. And now comes my law of sines. So I'm going to set up the triangle again, use my law of sines, and I can get 4.97 degrees for theta. That's not my bearing, though. Remember, if I had a bearing of 4.97, I'd be up here. So I'm going to have to add something to that as I think about it. So that would have been close to 180, but 4.97 away from there. We got to do a little bit of geometry in there to get our pieces together, right? And there we go.